All right, we're back after an accident with the chair. So we've just finished divisibility and what it means to divide into. So there are some common tests for some of the numbers, and the reason I'm presenting these to you is we're going to be working with the natural numbers, and these are like the most common numbers that you end up working with. So what are the quick checks to see if a number is divisible into another number? Well, 2. The last digit is even. What that means is if you're looking at a number and the last digit is 0, 2, 4, 6, or 8, then what you have is an even number, and 2 will divide into that number guaranteed. I think that's probably one we're all kind of familiar with, but if not, there it is for you. How do I know if 3 divides into a number? Well, a real quick check to see if a number is divisible by 3 is you add up the sum of the digits. Okay, so looking at the number, you just add up the digits. We're going to do this in just a minute, so you'll see what I mean. And that will probably give you a smaller number than you started with. And if that's divisible by 3, then the original number is divisible by 3. If something's divisible by 4, then you look at the last 2 digits, not the last one, the last 2 digits, if they are divisible by 4. You know something's divisible by 5 if it ends in 0 or 5. Okay, that would lead me to have no remainder. Something's divisible by 6 if it is divisible by both 2 and 3. So you would do both those checks. It's divisible by 8 if the last 3 digits are divisible by 8. So again, we're thinking that we have a larger number. We're trying to break it down into something smaller that can be checked real quick. 9 if the sum of the digits is divisible by 9. 10, it ends in 0. And we'll finish with 12. It's divisible by 3 and 4. Hey, you might be thinking, hey, Perkster, you skipped 7 and you skipped 11. Are there tests for those? And in fact, there are number theory tests, but they're a little bit more advanced and they're not worth the trouble for those. So exercise 1, I'm just going to run through for us to try to build a little familiarity with these tests. I know we have calculators and we can do that real quick, and I get it, and use your calculator. Just trying to help you be able to think through these things and be predictive and maybe even avoid wasting a little bit of time. So we're going to use the rules for divisibility to determine if the following is true or false. Okay, so and then we'll state the reason. So here we go. Does 4 divide into 3,754,084? Well, that's a large number. I don't feel like doing that long division, but the good news is to test for divisibility by 4, I just look at the last 2 digits. So I'm just going to look at the 84, and I'm going to ask, okay, is 84 divisible by 4? If 4 divides into 84, then it divides into that whole big number. Okay, so let me come over here, and you can probably tell without even doing the division, but I'm just going to be thorough here. Does 4 divide into 84? Well, 4 goes into 8 twice. Leaves me 0. I bring down the 4. 4 goes into 4 once. And I have a remainder of 0. So 4 goes into 84 21 times. So this one is true. And why is it true? Well, it's true because 4 divides into the last 2 digits. That's the test of divisibility for 4. Okay, works every time if that is the number that you're curious about, whether or not it divides into another number. Okay, the next one. This will help answer any question you have about the divisibility test for 3 or for 9. 9, does 9 divide into 4,119,706,413? That's a mouthful. Well, I don't want to do that division, and I don't have to. Here's what I am going to do. I note that the divisibility test for 9 is I take the sum of the digits, and is it divisible by 9? Okay, the sum of the digits just means I'm going to add this up, and you're going to help me just so that we're all doing this. It's 4. I add 4 plus 1. What's 4 plus 1? 5 plus 1. 6 plus 9. 15 plus 7. 22 plus 0. Yeah, we all got that one. 22 plus 6 is 28. 28 plus 4 is plus 1. And finally, plus 3, that gives me a total of what? 36. Well, again, we can probably see that right off the bat from multiplication tables, but I'm just going to do the work here to be thorough. Okay. The sum of the digits is 36. Does 9 divide into 36? Well, it does. It goes 4 times. There's no remainder. So does 9 divide into this very large number? Well, that is true. If you like math, I don't know if you do or not, but if you develop a liking for math, the proof of the divisibility test for 9 is really clever and cute, but it requires some background knowledge. I can't just do it for you right now, but anyway, it's fun stuff. So finally, 8. Does 8 divide into 677,838? Well, saying divisibility a lot gets to be a mouthful. Sorry about that. The divisibility test for 8 is I look at the last 3 digits. I'm going to look at the 838. Okay, so we'll come over here, do this work. 838, I need to know, is it divisible by 8? 8 goes into 8 once. So far, we're looking so good. No remainder. I bring down the 3. 8 does not go into 3, so I'll put a 0 up there and bring down the 8. And 8 goes into 38. Well, it does that 4 times, but here's the unfortunate thing. It leaves a remainder of 6. And remember, the definition of divisibility is if I can divide the number in and there is a remainder of 0. So when I divide 8 into the last 3 digits, 838, I can do that 104 times, but there is a remainder of 6. So this is false. 8 does not divide into that big number. We doing all right? You tracking with me on that? All right, well, let's flip the page. There's a problem on the next page for you to do, which is, or actually there's not, but you're going to do the last 2. I guess I just had one exercise on this. You're going to do those last 2. Determine D, is that true or false? Does 5 divide into that large number? And then E, does 6 divide into that number? Well, first, real quick, I'll give you time for the last one, but the first one, D. We don't even have to do any calculating. Does 5 divide into 562,122,835? Yes or no? Yes. Why is this one right here true? What's the reason? It ends in 5. Yeah, just that easy. So if you did do the division, then that's fine. But I'm just trying to make it quicker than actually doing the operation. All right, so I'm going to give you another 30 seconds or so to finish up the E problem. Does 6 divide into that? So what is the divisibility test for 6? How do you know if a number is divisible by 6? 2 and 3. Okay, so it doesn't matter which one you start with. I'm going to start with 2. Is this number here divisible by 2? Why not? How do I know that without doing anything? Yep, the last number is 3. It is not an even number. So 6 does not divide into that. So that's a false statement. And then the reason is 2 does not divide into the number? There are shorter ways that you could have answered that, but that's just the way that I am going to express the answer to that. We doing okay with the divisibility tests? You're going to do some of those on your homework. You're going to practice them. You're going to be like, oh, that's pretty cool. And then you're going to move on. So then the next thing after we talk about divisibility is you will end up noticing that there's going to be numbers nothing divides into. Those numbers are called a prime number. What a prime number is it's a natural number greater than 1 that has only itself and 1 as factors. Okay, so prime numbers have only 1 and itself as a factor. So for instance, the number 3. 3 is a prime number. There's nothing that divides into it except for 1 and itself. So just to give us a little fun thing to do to talk about prime numbers, what I did is I looked up, or I remembered, we're going to use what's called the sieve of, now I'm going to mispronounce this because I have a very large tongue apparently, Eratosthenes. Okay, the sieve of Eratosthenes. Eratosthenes was a Greek mathematician, and he came up with this simple little procedure to figure out the list of prime numbers, and we're just going to use it here to figure out what numbers are prime less than, what are the prime numbers less than 100. So I'm going to try to get as much of this table on the screen as I can, and here's what you do for this particular sieve. Okay, so first thing is I'm going to cross out 1. 1 is not a prime number by definition, so I'm going to cross out 1. So what that means is the first prime number I have is 2. Okay, 2 is the first prime number. 2 is only 2 times 1. There are no other factors. There's nothing else that divides into 2. So here's what the sieve is. The sieve is just a procedure. It's just a fancy word for a procedure. What I'm going to do now is I'm going to go cross off every second number. Okay, since 2 is prime, that means 1, 2, 4 cannot be prime because 2 divides into 4. And so then 1, 2, 6 cannot be prime because 2 divides into 6. And then 2 more is 8. So I'm just going every second number now. Does that make sense? So this takes a second. So I'm going to now cross off every second number. Every number that I'm crossing off is not prime. So 10 and 12, 14, 16, 18, 20, yada, yada, yada. You don't need to hear me talk about it. We're all just crossing out every second number here. Okay, I'm almost exhausted from it, but here we go. There we go. Okay, so I've crossed off every second number. So now I have reduced my list of potential prime numbers by half. So now the next number, this is what the sieve tells me. The next number is 3. 3 is a prime number. And so now I'm going to do the same thing. What I'm going to do is I'm going to go through and I'm going to cross off every third number. That would be everything that 3 divides into. Now you're going to notice as you go through, some of these numbers are already crossed off. Okay, but that's fine. So I'm going to count every third. So the next one, 1, 2, 3 is 6. It's already crossed off. The next one, 1, 2, 3 is 9. So we'll cross it off. Then 1, 2, 3, 12 is already. Then 15 will cross off. 18's already crossed off. 21, then 24, then 27. And again, I'm not going to count them all out. 30, 33 will cross out. And so you can just follow along counting by threes. 36, cross off 39, 42, cross off 45, 48, cross off 51, 54, cross off 57, 60, so 63, 66, 69, 72, then 75, 78, 81, 84, 87, 90, 93, 96, and 99. Whew. Okay, so we're crossing off great gobs of numbers, which is good. I don't want this to take all day, but I just want you to see how we can, a procedure, like if I wanted to program a computer, how we would program a computer to find a list of prime numbers. So now what's the next uncrossed number? The next uncrossed number is 5. So 5 is the next prime. And so then I'm just going to cross out all the multiples of 5. So 10 is already done, 15, 20. Get rid of 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, and 100. And so we just go like this. So I'm just going to give us, I'm not going to talk anymore. I'm just going to give us a couple minutes to just go through. And then what I'm going to do is I'm going to list the prime numbers that are less than 100. And you could do this for a much larger list. But again, I'm not trying to bore you to death. I'm just trying to show you something that, from history that is pretty clever as people began to think about numbers and their structures. So 7 is the next one. And you're going to cross out every multiple of 7. So 14, 21, 28. 2, 9, goodbye. 6, 63, 70, 77, goodbye. 84, 91, goodbye, and then 98. So we got rid of a few more. The next one is 11. We'll cross off all of the multiples of 11. So that's 22. This is nice. They're all in a diagonal, 22, 33, 44, 55. 7, they're all done. The next one's 13. And so 13 more than that's 26, and then 39, and then 52, and then 65. We've got all these, and then 78, and then 91. Good. The next one's 17. And so then that would be 34 and 51 and then 68. And then so you see we're encountering that a lot of the numbers here are already crossed off. So I think actually we might have already found it, but I'm going to verify just a couple more with the list that I've already done. So 17 more than that is 78, 85, and then 9. So that gets too much bigger. So then the next one is 19. Then we've got 23 and then 29. I'm just going to go ahead and circle the primes. And if any of these are not prime, I'll tell you when we would have crossed them off. So then 31, but I think we've got most all of them. 41 and 43 and 47. 53 is prime, so is 59. 61 is prime, so is 67. 71, 73, 79, 83, 89, and we did it, 97. We went as far as we needed to go with the sieve, and we got the prime numbers. So there's a lot more prime numbers. In fact, there's a math theorem that's pretty easy to prove that there is an infinite number of prime numbers. There's no largest prime number, but the ones that we've found, probably the most common ones you will encounter is this list right here. I'm just going to write down the numbers that we just circled. So we've got 2 and then 3 and then 5, 7, 11, 13, 17, 23, etc., 31, 37, 41, 43. So when you're doing your homework and you're doing some of these problems that we're going to finish up our section with that involve primes, these are the numbers that you're going to be focusing on. You don't have to worry about other numbers. And again, I'm not trying to math torture you, so I'm not going to be incorporating huge, ginormous waste of your time primes. Now, while you're writing that down, I don't know how much you read the news, but this is something that just happened. So, oops, my Google search went away. On October 21st, because mathematicians have weird hobbies, on October 21st, a new largest prime number was found. And so I'm just going to show you my Google search right here. So hopefully my smoking hot wife doesn't text me anything weird. I should probably put this on airplane mode, but we'll see. So the new largest prime number is 2 to the power of, what's that power? 136,279,841, that number minus 1. The number of digits in that number is 41,000,000. 24,320. So it would take a long time to find it. It took a computer, a supercomputer, not just a PC. It's the first prime number found by a supercomputer, not just a desktop computer. Took it a year to do the calculations to figure that out. And the reward for it was $3,000. There's a mathematical prize for every new largest prime. I just thought that was interesting that one was found so close to us. So if you have, a year and you got access to a supercomputer, okay, you can make a little money and you can find the new next largest prime number. So math stuff is interesting. All right, we're flipping the page. Well, if I have a number that is a prime number, well, then what does it mean if a number does have other divisors, not just one in itself? Well, a number that has other divisors is called a composite number. A composite number is a natural number greater than one that is divisible by some other number other than one and itself. So what we're going to do, we're spending the rest of our time, is we're going to break down some composite numbers into their prime factors. This is a process called prime factorization. And then we're going to use prime factorization in a couple of useful ways. So for instance, this is going to be my example, and then I'm going to give you, you're going to do the next one. We're going to find the prime factorization of 700. Okay, so what we're going to do is we're going to use what's called just a factor tree. A factor tree just means I'm going to draw a couple lines right here. And we're going to determine what are two numbers that give us 700. It doesn't matter what two numbers, you can't go wrong. Okay, so like if you might say, Perkster, I would have picked a different pair of numbers. That's okay. We will always end at the exact same thing without a doubt. So I'm just going to say 700 ends in a 0. So I know 700 is 70 times 10. Now, your thought process might have been, well, 700 is even, so 700 is 350 times 2. That would have been great. That would have been a beautiful first start, okay? Now, I'm going to focus on the number 70 for a minute. 70, again, ends in 0, so 70 is 10 times 7. And what you want is at the end of every branch, you want a prime number. If it's not a prime number, you keep going. So 10 is 2 times 5. 2 is on my prime list that we just took a painfully long amount of time to develop. So 2 is prime, and 5 is also on that list. 7 is another number on that list. This 10 right here, 10 again, is 2 times 5, and now those are primes. So once you get a prime number, I like to circle it so that I remember it. That's just a way of me knowing that I don't have to do any more with that branch. Are you with me on what I did here? Okay, I don't want this to be complicated or confounding. I'm hoping prime factorizations are nice and smooth and easy. So then what I'm going to do is I'm just going to rewrite the number 700 as its prime factors. And you don't have to, but generally this is done in number order to make them easier to read. So I've got 2 2s, so that's 2 to the second power. I've got 2 5s, so that's 5 to the second power, and then I've got a 7. So 700 can be broken down into its component parts of 2 squared times 5 squared times 7. If you throw that into your calculator, it'll give you 700 if you want to double check me. What I would like you to do is right below that, I would like you to do exercise 3. Do the same process for the number 120. Okay, so 120. Somebody give me, there's no wrong answer here, unless the numbers don't multiply to 120, but somebody give me where you started. What factors did you use for 120? What was that? Okay, perfect. 20 times 6. If you use something else, don't worry. We will have the exact same thing. If your end answer is different than my end answer, that means there's a problem. But it shouldn't be because it's all the same factors. So if you did 20 times 6 or 12 times 10 or 2 times 60, all of those are great choices. 30 times 4, all of them are good. So here 20 is going to be, I'm going to go 5 times 4, or you could have done 2 times 10. Again, there's no wrong answers. We will end in the same place. 5 is prime. 4 is 2 times 2, which each of those is prime. Up at the top, 6 is 2 times 3. No choices there. And so that means 120. However you did it, you should have 1, 2, 3 2s, 2 to the third. Everybody get 3 2s, no matter how you broke this down? Okay, I just want you to see that there's no wrong first step here. If you didn't do 20 times 6, you're going to end up in the same place. Then I have a 3, and then I have a 5. Okay, so now what we're going to focus on is, okay, we've got this idea of finding the prime factorization. How can this help me? Why even bother with this? And that is a great question because we don't want to just waste our time here. So we're going to do 2 quick things. The first thing is what's called the greatest, if I can spell greatest, the greatest common divisor. The greatest common divisor is the largest number that divides into both numbers. So I want to find a number that divides evenly into 2 numbers. So for instance, my example right here, I'm going to do an example, you're going to do an example. My example is this. We're going to find the greatest common divisor. We're going to find the largest number that divides into both 216 and 234. We can see they're both even, so we know 2 divides into both of them, right? But is that the largest number? Can I find something bigger? Well, great question. So here we go. That's what we're going to do. So first thing, 216. I'm going to do the prime factorization of 216. Well, I see that 216 ends in 16, which 4 goes into. So 216 is 4 times. Just going to use my calculator. 216 divided by 4 is 54. Oh, good. I've broken that down into numbers that I'm more comfortable with. 4 is 2 times 2. Both of those are prime, so I'm going to circle them. 54 is 9 times 6. 9 is 3 times 3. Both of those are prime, so I'll circle them. And 6 is 2 times 3, both of which are prime, so I'll circle them. So I'm just going to come over here to the right side of my page, and I'm just going to summarize that 216 is, I've got 1, 2, 3 2s, so 2 to the third, and then I've got 1, 2, 3 3s, so 3 to the third. Now I'm just going to do the same thing with 234. So 234, I'm going to just come over here to the side a little bit, 234. 234 is even. So I'm just going to say, okay, 234 is 2 times something. So let's see. 234 divided by 2 ends up being 117. 2 is prime. 117, those digits, 7, 8, 9, add up to 9. So 117 is 9 times something. 13. 13's prime, that's great. And 9 is 3 times 3, which are both prime. Now, when I give you a problem like this on the test, and I'm pretty sure I mean, I know I previewed the problems on the homework, and the ones that I saw, I'm not trying to give you any weird prime numbers, okay? So just know that the rules for divisibility, I gave those to you because they should be helpful in doing this sort of thing quickly. And so we've got 234 is equal to 1, 2, 2 3s, and 13. And so you're thinking, okay, that's great, Perkster. I can see how to do that, but what do I do now to get the largest number that divides into both of these? So to find the greatest common divisor, okay, the GCD, here's what you do is you take the smallest amount or the smallest number of each common prime. You need something that's in both of them. So they both have a 2, right? But 216 has 3 2s and 234 has 2 2s, or excuse me, has 1 2. If I for my greatest common divisor, if I took all 3, if I took 8, 8 is not going to divide into 234 because 234 only has 1 2 in it. So that's why I take the smallest number of each common prime. So I'm going to take a 2. They both have 3s. But again, 234 only has 2 3s, has 9. I can't take more than that because if I take an extra 3, if I took 27, 27 is not going to divide into 234. And your calculator can verify that for you. So then I'm going to circle that, 3 squared. And then they don't have 13 in common. So I'm not going to include 13 because if I did, 13 doesn't divide into 216. It's not part of that number. So this right here, 2 times 3 squared, is going to be the greatest common divisor. 3 squared is 9 times 2. That means number 18 is the greatest number. There's nothing bigger. It's the biggest number that divides into both of those numbers. And you can test that on your calculator. 216 divided by 18, no remainder. 234 divided by 18, no remainder. So exercise 4, I'd like you to do the same thing with those two. You're going to do the prime factorization of those two numbers, and then you're going to find for me the greatest common divisor. right, so let's go through the busy work here. So finding the greatest common divisor. So again, I'm finding the largest number that will divide into both 225 and 825. So 225, this is how I broke it down. You might have done different, but we will end in the same place. I got 5 times 45, so I ended in 5. 45 is 5 times 9, and 9 is 3 times 3. So 225, however you broke it down, is 3 squared and 5 squared, those two things. 825, I see it ends in 5, so it's 5 times 165. I see 165 ends in 5, so it is 5 times 33. And 33 is just 3 times 11. So no matter how you broke it down, where you should end for 825 is it is 3 times 5 squared times 11. Okay, that's the busy work. Once you do that, the greatest common divisor is real quick to find. You just take whatever they have in common, you take the smallest amount. So what they have in common are 3s. So I'm going to take 1 3 because I need whatever I pick to divide evenly into both. And then I can pick 2 5s from either one. It doesn't matter. So 5 to the second. I don't pick the 11 because the 225 doesn't have any 11s. So 11 is not going to divide into 225. So that's why I don't pick that. So now the greatest common divisor is 25 times 3, and 25 times 3 is 75. So you can check with your calculator, verify this. 75 does divide into both 225 and 825, goes evenly, and it is the largest number that does so. All right, so when we flip the page, our next two problems are going to use the work that we've already done. What we're going to talk about next, the other thing, is what's called the least common multiple. When we do go to talk about fractions, the least common multiple is actually how you find the common denominator for fractions. So that is where this becomes useful. The least common multiple is the smallest number that the two numbers will divide into. So what we're going to do is we're just going to make use of some busy work we've already done. We're going to find the least common multiple of 216 and 234. What's the smallest number that both 216 and 234 will divide into? So what I'm going to do is I'm just going to go back to the previous page and I'm going to find my busy work. What are the prime factorizations for these two numbers? And then I'll tell you how to find the least common multiple. So 216 from the previous page was 2 to the third and 3 to the third. So I'm just going to transcribe that onto this page. And then 234 from the previous page is 2 times 3 squared times 13. And to find the least common multiple, what you need is you need the most of every prime, factor. If both of these numbers are going to divide into a bigger number, then it has to have all of the prime factors we see. So the least common multiple, the LCM, is going to be, well, the most 2s I see is 2 to the third. The most 3s I see is 3 to the third. And then the most 13s I see is just 13. So you take the most of every single prime factor. That gives you the least common multiple. And when I go in my calculator and I do that, we've got 2 to the third is 8. 3 to the third is 27. 8 times 27 times 13 is 2,496. That is the smallest number that both 216 and 234 will divide evenly into. Yeah. Yep. Yeah, it's exactly reverse of what you think. This is how I remember it. Honestly, I have to think this through. For the greatest common divisor, you take the smallest amount. Okay, instead of greatest, you take the smallest amount of each common prime. For the least common multiple, you take the most. So instead of least, it's the most of every prime. Okay, that's the most simple way that I can say it to you. So exercise 5. Exercise 5 makes use of the prime factorizations from the bottom of the previous page. So transcribe that over. All right, so from the previous page, 225 is 3 squared and 5 squared. 825 is 3 and 5 squared and 11. So the least common multiple, for the least common multiple, you take the most of every factor. So I'm going to take 3 squared, that's the most 3s. I'm going to take 5 squared, that's the most 5s. And then I'm going to take 11, that's the most 11s. I don't have to include any other factors. Including any other factors is how you get other common multiples, but they're not the least common multiple. Okay, so we're just interested in minimizing here. So 3 squared is 9, 5 squared is 25, times 11. So 9 times 25 times 11 is 2,475. That is the smallest number that both 225 and 825 divide evenly into. Okay, just 2 more problems. We're almost done. Thank you. You're doing great. Exercise 6, I give you 2 new numbers, and I'm asking you to find the least common multiple. So I'm going to give you a couple minutes. In about a minute or so, I'm going to start the busy work, and then we'll talk about the answer. All right, so just running through my prime factorizations here. For 144, I picked 12 times 12. You could have picked 4 times 36. You could have picked 2 times 72. Doesn't matter. However you did that, you're going to end up with 144 is 2 to the fourth times 3 to the second. For 300, I started with 10 times 30. Again, there's like a dozen options you could have started with. 10 is 2 times 5. 30 is 5 times 6. However you did it, 300 becomes 2 to the second times 3 times 5 to the second. The least common multiple, you take the most of every single factor. So for 2's, I'm going to take 2 to the fourth. For 3's, I'm going to take 3 to the second. And then for 5's, I'm going to take 5 to the second. And when I throw that down in my calculator, 2 to the fourth is 16. 3 to the second is 9. 5 to the second is 25. And that is 3,600. 3,600 is the smallest number that both 144 and 300 divide evenly into. All right, last but not least, just to give you a pair of numbers that are more common when you're dealing with fractions, I've got the numbers 18 and 30. So go ahead and find both, just so that we have to differentiate. Find both the greatest common divisor and the least common multiple of 18 and 30. All right, so let's run this down. If you have any questions, comments, or concerns at all, please let me know. So 18, again, it doesn't matter. I'm going to do 2 times 9 because I see 18 is even. 2 is prime. 9 is 3 times 3. So there we go. So 18 is 2 times 3 to the second. There's 2 3's. There's 1 2. 30, 30 ends in a 0. So I'm going to say, okay, that's 5 times 6. 5 is prime, 6 is 2 times 3, and so 30 is 2 times 3 times 5. So the greatest common divisor, remind me, because now we're doing them both together. What is my process for the greatest common divisor? The least of the ones in common. Well, I mean, you can just say the least, because the least of 5's is having no 5's over 1 5. So to even simplify it more, the greatest common divisor is the least. Okay, so the least 2's is a 2, the least 3's is a 3, and the least 5's is not having a 5 at all. So the greatest common divisor, the largest number that divides into both 18 and 30 is 6. Which that's kind of easy to verify with your calculator. So like 8 doesn't, there's no larger number. So I'm not pulling one over on you. The least common multiple. So the process for the least common multiple is I take the most. Okay, so the most of each of these, well, the most 2's is 2. The most threes this time, I'm just going to put a check mark by it this time. So the most twos is 2, the most threes is 3 squared, and the most fives is 5. So we have 2 times 3 squared is 9. 9 times 5 is no, I'm sorry. 2 times 3 squared, that's 2 times 9 is 18. That's better. 18 times 5. 18 times 5 is what is that, 90? All right. And 90 is the largest, or excuse me, the lowest number that both those divide evenly into. If we were dealing with fractions and adding and subtracting fractions, 90 would be the common denominator that you would use for those two fractions.